of this overview of ACI, which is Cisco's newest infrastructure technology. And it comes out of the world of SDN. And there's a lot of hype in the SDN sphere. There are some misnomers, perhaps even some misunderstandings in the world of SDN. And that's fine because it's a catch-all phrase. But Cisco's particular response to the SDN trend is this system they call the Application Centric Infrastructure. And my goal today is to give you guys enough of an understanding of Cisco's ACI so that you feel more comfortable with it. A lot of companies we find have purchased the equipment that works. It'll actually support the ACI environment, but they haven't necessarily stood it up yet because there is a bit of a paradigm shift in the way things are done in this new fabric infrastructure. And so one of the goals that I've not only developed for this webinar, but in general with my customers, is to really help them to understand what is different and what's not, and how to leverage your existing engineering skill sets in this new world which is yet to come. So, for most of us, we understand that Cisco dominates the infrastructure space. They may not dominate the storage space. They actually are the #1 blade server system provider in North America. That was kind of an unexpected feat. But in the infrastructure space, they really are probably, along with Juniper and a couple of other companies, the most commonly found switching, routing, infrastructure vendor, at least here in North America and in Europe. And, about 8 years ago, they came out with the Nexus data center switching line, which is still alive and well. And in fact, back then, they came out with something called and this is my whiteboard, folks, hopefully everybody can see it. We had the Nexus 9000, I can take that back, the Nexus 7000, and the Nexus 5000 switches were the two most commonly deployed. And along with that, we had another technology, which was the FEX technology, which was the Nexus 2000 line. So most of you have built data center architectures that are comprised of core, aggregation, and access layer switches, which are, for the most part, Nexus-based. Right? So here's your FEXs, hanging off your access layer switches, which are typically 5Ks, and then at your aggregation and at your core layers, you find usually the Nexus 7000. Now there is a Nexus 6000, there's a software switch called the Nexus 1000, there are Nexus 3000s, which are ultra-low latency switches. And then Cisco came out with this new product called the Nexus 9000, and that's what this webinar is about. This webinar is about the Nexus 9000 specifically running in ACI mode. And again, what are its operational benefits? How the automation and orchestration works in this paradigm, which is of great benefit to the efficiency and optimization of our management of this kind of infrastructure. So you'll see in this webinar that we can actually coordinate configuration tasks through third-party hypervisors. In fact, I should probably amend this slide and say, how does it integrate with third-party hypervisors and layer 4 through 7 services? Because ACI will talk to vCenter, which is the VMware controller. Yes? Oh, I thought I heard somebody speaking. The ACI system will integrate with VMware. It will integrate with Microsoft Hyper-V environments, and it will integrate with KVM environments. And ACI will talk to things like F5 load balancers, checkpoint firewalls, intrusion detection systems, any layer 4 through 7 service that has what's known as a device package can actually be controlled by the same APIC or controller in ACI that actually also configures the infrastructure. We're going to get into the details of this shortly. And then again, I just want to make sure that everybody can gain an appreciation not only of the things that are different, but of the things that haven't changed, right? Because let's take a little bit of the sort of intimidation out of this balloon and show you guys that ACI, although it's slightly different paradigm, software-defined networking like, everything we've learned over the past 15 to 30 years as network engineers doesn't automatically disappear. In fact, we probably have more job security than ever because the amount of complexity that's actually running in the environment, it's still all routing and switching based. And the big difference here is something called the policy-based framework. So that's what we're about to get into here on the webinar. So software-defined networking is a jargony term that's been floating around for 5 to 8 years. And it comes out of Stanford. I won't get all nerdy on you. But it's become this sort of catch-all phrase or umbrella term that is meant to describe this trend we're seeing in the network where the network infrastructure environment is becoming as flexible and as agile as the server environment has in the past 15 years, right? VMware changed the world, okay? The game was fundamentally and forever changed when we were able to put multiple operating systems onto the same physical server. And now there's a lot of different options in that sphere, but VMware started it off. That type of agility and flexibility has never really existed in the network. In fact, if you think about it, on a switch, on a classic switch or router, either of the two, or let's say it's a multi-layer switch from any vendor, Cisco, okay, Juniper, what have you, there is going to be an operating system that is installed physically local to that switch. In the case of Cisco, it's called the Nexus operating system. And that operating system comes with features, right? So let's take a classic one, OSPF, right? OSPF means that I can run a routing protocol. Well, if Cisco didn't build in that stack, into that stack, that process known as OSPF, which hopefully they've conformed to the open standard successfully on, that switch is not going to be able to connect to another, and really this is at layer 3 if we're talking about routing, so I should say that router is not going to be able to connect to another and run the OSPF routing protocol unless that feature is built into the Nexus operating system. That's very locked down. That's a very limited paradigm, right? Because let's say some new cool feature comes out, we have to wait for the vendor to decide that they want to actually implement it. And we have to wait for that new version of the operating system. Whereas, what if that system was open? What if that switch didn't have a vendor-specific operating system, but in fact, it was just a commodity piece of hardware that could do anything? And you had some switched infrastructure, and then alongside of it, you have this server called the controller. And in the controller, you can create or determine the flow of traffic in your network based on any set of parameters you so choose. And then what happens is that the controller will actually send or program those switches, these days probably using a protocol called OpenFlow. And it will actually program the flow tables. You know, what we typically associate on the switch or a router as a MAC address table or a routing table is a database that tells that device what to do with packets or frames when they come in. Well, the controller will now program the switch or the router, whatever function we want. It will program those flow tables dynamically, but from a central point of configuration outside of the actual infrastructure. This is called separating the control plane from the data plane. It also, on these switches, if they just become basically Linux switches, or something that's open source, we can actually begin to write programs to do things that never existed before. We don't have to wait for the vendor to decide they want to implement some newfangled thing, we can actually just test it out on our own. If you've got software development in-house, sky's the limit on what you can do on your network infrastructure. This is absolutely positively a game changer, right, guys? Think about it. You know, you can write an app for the iPhone. Anybody can go write an app for the iPhone. It's an open ecosystem, right? Well, not anybody could previously go write an app for a Cisco router, but today you can, at least in theory. And it actually depends on the vendor. Companies like Brocade actually have pure SDN plays. Cisco, on the other hand, came up with what we call Application Centric Infrastructure, which is a little bit of a shift on this, because instead of having this controller be the control plane, Cisco said, you know what? These switches are powerful. So if we build an architecture, and we do so with these terms called spines and leaves, so the switches either play a role in this fabric of either being spines or leaves, and then this becomes the ACI fabric. And then to this fabric, we connect a controller that's called the APIC. And we connect servers to the fabric. These are known as endpoints. We can also connect things like firewalls or load balancers as endpoints. And what you're going to see is that the APIC is programmable in what we call a northbound way, which means things like UCS Director or OpenStack can program our controller in the Cisco fabric. Or the APIC also synchronizes or integrates with third-party appliances like firewalls and load balancers, and we can actually program those firewalls and load balancers from the APIC as well. But fundamentally, the difference between Cisco ACI and SDN is that the Cisco controller is actually a policy database. It is not a control plane. So we still run what's known as an ACI mode operating system on these switches. And these all have to be what are known as Nexus 9000 switches. You have to have the proper hardware that is supported in ACI mode. And you have to install a different operating system. This is not the Nexus operating system, but it is an operating system. Meaning that the APIC will actually send instructions to the switches, and it will configure them. But once they're configured from that central point known as the APIC, they will actually run their own processes. So they don't give up the control plane. Cisco's argument, guys, is that if you put everything on this external controller in terms of determining the control plane, you're going to bottleneck the controller. Even if you have a cluster of controllers, you're going to bottleneck the control plane on those servers that you're calling controllers. Whereas here, what we're actually doing is instead, we're defining the policies that we want in place on this infrastructure. And those are stored centrally on the APIC. And then the APIC will configure the infrastructure dynamically to support the policies. But the infrastructure equipment is still running an operating system that's capable of things like OSPF, or in fact we use something called ISIS in our VXLAN underlay. We're going to get into the detail of that in just a little bit, but I want you to understand that the approach is different from classic SDN. Does that make sense? Any questions or comments on that so far? I'm keeping an eye on that chat window. Cool. Thank you. All right. So, why the hubbub? Why is this? Aside from the fact that you can see that there's a certain kind of centralization that's happening here, how is this actually really going to affect the operation of the network? So let's think about a traditional environment again. See if I still have my traditional environment here. Yeah, sort of here, right? So let's say here's my, again, here's my traditional data center. And if I want to deploy a physical server, or any kind of server, what happens is the network team has to provision a port on the access layer switch. And the FEX is really just, by the way, for those of you who don't know, the FEX is a port expander on the parent switch that's connected to it. It just becomes a slave. So the ports on the FEX are actually controlled by the parent switch it's attached to. And by the way, there's a question from James. Are you able to lose the APIC and still continue to operate? Absolutely, yes. And it may be confusing that I've only shown a single APIC in my drawing. There's absolutely going to be a cluster of APICs. You can't actually buy an ACI fabric with less than 3 APICs. So you're actually going to dual home your APICs. You're going to have 3 APICs, and you're going to probably spread them out over different leaves. Actually, you wouldn't technically be able to do that. But you would spread them out over different leaves so that you don't actually have an environment without an APIC. But even if you were to lose all 3 APICs, your fabric would still continue to operate. You wouldn't be able to make changes to it, but you would still be able to function. Your production traffic isn't going to die just because your APIC died. So when I draw in a single APIC, guys, and it's only single connected, I do so for simplicity purposes on the whiteboard. Please understand that that is a cluster and that I'm representing only a logical depiction of it, but really behind this one single APIC is a cluster of 3 dual-homed APICs into your fabric. Cool? All right, so getting back to the other traditional environment, what's going to happen is that when you deploy a service, what happens? Server guys come to you and they say, we want to stand up a new app. Well, they've got to coordinate with you. You've got to create a VLAN, right? So you've got to add a VLAN on probably each one of the switches manually. If this is, in fact, like a totally new application, right? You probably didn't have that VLAN before. If you've got a firewall, you've got to add a new policy. If you have a load balancer, you've got to go in and something that, you know, the load balancing, or the server team usually has the load balancing. They've got to go in, and the F5 team or the Citrix team's got to go add a policy. The security team's got to go add a firewall policy. You might be doing access lists. You need to make an access list change now on the switch. And what about if you have QoS? You've got to go change your QoS policy and apply your QoS policy differently on each one of these switches. And if you have to do this all manually, and today in most cases, even if you're using scripts to do this, it's still a process of connecting to each one of those switches, making those changes. And as you know, we're human beings. We can make mistakes. We can fat finger something, right? We can actually break something in the process of trying to amend the config, right? If you go in and make a change in a QoS policy, what if you accidentally broke something else, okay?
Yeah.
Aside from the fact that you've got all this manual work that needs to be done, a lot of different touch points.
Tim, do you see the question from Yo Handy?
I do not.
Does the APIC use OOB network to connect to the spine and leaf switches?
Yes and yes. Who asked that question?
Yo Handy.
You're handy. So back over here to the picture of my fabric, we absolutely have the option, not the requirement, to connect. Of course, all of those Nexus 9Ks have what's known as a management interface, which can be used to connect to an out-of-band infrastructure, and your APIC as well can connect to the out-of-band infrastructure. However, unlike a lot of other infrastructures, it's not absolutely critical. Todd, we are recording this presentation, so you'll be able to review it again later. So the Switches, yes, they can be, but they do not require to be, and I'll explain why in a little bit. Okay, and it's because we actually have so the APIC has layer 2 connectivity via the fabric directly. So the APIC is an endpoint in the fabric, and it's able to communicate with the switches directly without any IP addressing. The APIC can communicate with all the Nexus 9Ks, and in fact, the way we first initialize the fabric can only be through the APIC. The APIC will need out-of-band management connectivity because you're going to have some management desktop connected to the out-of-band portion of the APIC, and then you're going to use HTTPS to open up a GUI known as the APIC. So there's a GUI, which is called the APIC, on this physical server. It's a C-series server, by the way. And you'll use the out-of-band connection to open up the GUI. Optionally, you can connect those 9Ks out-of-band. So back to this environment up here. A lot of manual work and prone to a little bit more error when you want to stand up a new service in a traditional environment. As powerful and fast and extraordinary as that environment may be, there's still a lot of work involved. And, by the way, this type of infrastructure, pretty expensive. Pretty expensive because you're dealing with flat layer 2 domains these days. And let me ask you guys the question, why are having layer 2 domains or the same VLANs all over my data center more important today than they've ever been? Because there was a while, 15 years ago, we were moving away from having all of those flat layer 2 domains. We were doing a lot more routing at our access layer. Why have we flattened out our layer 2 domains again? I'm not seeing any answers. Are answers coming in, Nate? It's strange to me that I'm not seeing all the Q&A. That's right, Todd. It has to do with virtualization, but more specifically, it has to do with vMotion, right? Because if you want to move your VMs between ESX hosts, we need layer 2 adjacencies. So we need the same VLAN everywhere in the data center, which means the TCAMs, or the hardware tables on our switches, need to be really large, which actually means they have to be really expensive. Do you guys know how much a Nexus 7K costs? Sometimes $250,000, $500,000. In the ACI fabric, we're able to significantly bring the costs down because the TCAMs on the leaves do not need to be as substantial, because reachability, even though we're entirely, absolutely, positively able to support 1 million endpoints in this fabric, and they can be layer 2 adjacent, we actually don't need giant TCAMs on our leaf switches because reachability is not based on customary layer 2 switching principles. And that I'm going to get into in just a few minutes, but I want to restate that. Reachability in this ACI fabric, I'm adding in a server here, server 3. For traffic to flow from server 1 to server 3, server 1 and server 3 can be on 2 totally different subnets. We actually don't need traditional routing or traditional switching between server 1 and server 3. Once that traffic from server 1 hits the leaf is going to build a tunnel called the VXLAN tunnel, and I'm going to get into the details of this, and it will encapsulate and carry any traffic, layer 2 or layer 3, between those 2 servers based on my policy, not based on routing or switching in a current Ethernet switching routing paradigm. There is routing and switching going on in the background of the fabric, but I assure you, if server 1 server 3 is 172.16.5.1. Leaf 1 will actually become the default gateway for server 1. Leaf 2 will become the default gateway for server 2. But besides that, there is just a tunnel that's going to be built between those two leaves, and we can send any traffic we want into that tunnel. And so we're able to maintain layer 2 adjacency, and therefore we're able to bring down the cost of the infrastructure. So the Nexus 9Ks, you guys, are the highest throughput, least cost switches in the industry currently. So obviously Cisco has an interest in still selling you hardware, right? That's how they've built their name. They're the plumbing of the enterprise and of the internet. For them to become truly a software company, they'd have to give up the manufacturing of hardware that their operating systems run on. Cisco's not quite ready to throw away what they've built their empire on. So they have leveraged their innovative engineering skills to develop infrastructure equipment which can move up to 30 terabits per second of traffic through a single switch. Okay. By the way, the Nexus 7018 can move 80 terabits of traffic. The Nexus 9518 can move 30 terabits of traffic. Those are both awesome numbers. Now, the Nexus 7000 is probably going to form the core of your enterprise. But here, in an ACI fabric, it's actually the combination of all the spine switches which forms the backbone of your infrastructure. So if you've got 4 spine switches, that's 120 terabit of throughput that you can push on your fabric. So you have to kind of think about it a little differently. The price per port has gone down for 10 and 40 gig interfaces. Cisco's made the purchase of these Nexus 9000s quite compelling to your CIO and your CFO. When they see, when it's time for a life cycle of equipment, and they see the price per port on these switches, it's going to be pretty hard to talk them out of it. So, in a sense, ACI is something that, or at least the Nexus 9000 infrastructure, is something that's almost unavoidable. Also, the watt usage, the power usage per port is the lowest in the industry. So, Cisco's won a bunch of awards on these, and they make it really, really hard to say no. And a lot of you guys probably have Nexus 9000s, and maybe you're not running them in ACI mode. You might just be running them in the standalone NXOS mode, which is an option, something I hadn't mentioned earlier, but you can run either version of operating system. You can actually run the Nexus 9000s as traditional switches and routers with Nexus operating system, or you can switch them over to the ACI operating system. When you do, everything is going to become policy-based. So let's go back to the whiteboard. I'm actually going to redraw my infrastructure again. There we go. Cool. So I've got spine 1, spine 2, leaf 1, leaf 2, leaf 3. You probably have the leaf 4, but I'm just going to keep it simple. All of your leaves connect to all the spines. All the spines connect to all the leaves. And if you grow out this infrastructure, I might as well add leaf 4 here. You have to connect leaf 4 to all the spines. If you begin to, and these are all 40 gig, if you begin to bottleneck on all those connections, which are going to be equal cost multipath links, you add another spine to alleviate the contention for resources, you've got to connect that spine to all the leaves. Does that make sense? By the way, if you think about it, if I have an endpoint here, let's say server 1 and server 2, there will only ever be a max of 3 hops between east-west traffic on the fabric. Right? It goes through a leaf, a spine, and a leaf. There's no other way. And as long as you continue to scale this out horizontally, all of your servers, all of your endpoints will never be more than 3 hops away from each other. Does that make sense? Aha. Is it disruptive to convert from a Nexus 9K NXOS to ACI mode? Yes, it is. You do have to reboot the switches. And you do have to reinitialize the fabric. Now, Cisco does have a guide or a best practice guide on how to do that so that it's least disruptive, but it's definitely a maintenance window. All right, so like I was saying, those servers are hanging on here as endpoints, and they're a max of 3 hops apart at all times, no matter how far you scale this infrastructure. And Cisco's vision of this thing is, currently, we support 200,000, over 200,000 physical ports for endpoints, and over 1 million servers as endpoints. Question from Prashant. Any mechanism for loop prevention? We do not run spanning tree in the fabric. We can run spanning tree at the edge, but we do not need spanning tree inside the fabric because it's actually all layer 3. And I'm about to show you how. You guys ready? All right, so check this out. First of all, reachability in this environment is entirely dependent on what we call endpoint groups. And on my slide here, you can see that endpoint groups can be identified by a number of different characteristics. So for example, I might say endpoint group blue is going to be defined by an IP address range of 10.1.1.0/24, right? That subnet is going to become endpoint group blue. Endpoint group green is going to be defined by VM name star.rnd.abc. So any VM that has, and there's a wildcard there, that has .rnd.abc in its name will be identified and put into this endpoint group green. Or I could define an endpoint group based on a VLAN, or a physical port, or any of these characteristics that I've listed here, even including DNS, MAC addresses. VLAN, port group, okay? And then what happens is, here's my APIC again, and remember I said my APIC has a policy database. Inside of my policy database, I'm going to build something called an application networking profile. And in it, I'll say EPG blue can talk to EPG green. And now, traffic will get automatically routed through the fabric between the leaves that those endpoints connect to. And reachability is not going to be based on routing how we normally think about it. Reachability is going to be defined ahead of time by this policy. Now, if you pick up and move physical server 2 over to leaf 3, guess what? The policy follows it. Server 2, it still has the same VM name. It's still going to end up in the same endpoint group, and reachability is still going to be permitted based on an application network profile. By the way, nothing flows on the fabric by default, so no traffic is allowed unless there's a policy set up for it. So also, if devices are in the same endpoint group, they can communicate with each other, but that's it. Either they have to be in the same endpoint group, like let's say servers 1 and 3 both were in EPG blue, they would be able to communicate with each other. And as long as I set up an application networking profile between EPG blue and EPG green, server 1 and 2 could talk to each other, as well as server 3 and 2, since servers 1 and 3 were in EPG blue and server 2 I said was in green, or at least I implied it. So far, so good, guys? So everything is going to be defined in what we call endpoint groups, and reachability is going to be defined by these endpoint groups. Now, it gets better. First of all, let me just really high level introduce the concept of a VXLAN. So VXLAN is when you take either a layer 2 Ethernet frame or an IP packet, and then you encapsulate it, it becomes the payload of another IP packet. So that means that I can route layer 2 or layer 3 traffic hidden inside of a VX. This is called a VXLAN packet. It's kind of like a GRE tunnel, if you know what that is. But the difference is there's actually a tag called the virtual network identifier. And just like VLAN tags give us isolation of traffic, but with VLANs you only get 4,000. With the VXLAN packet, you get 16,777,000 different VXLAN IDs that you can use for isolation. So for cloud service providers, this means a whole lot more scalability if you've got tens of thousands of different customers. Now, what VXLAN also uses is a new technology or a new term called a virtual tunnel endpoint. And what's going to happen is that the APIC is going to program each one of these switches to have their own unique VTEP. So let's just go ahead here and assign a VTEP address to each one of these switches. Let's say it's 172.16.5.1, 172.16.5.10, 172.16, whoops, 5.33, and by the way, these are all /32 host addresses. 172.16.5.200, 172.16.5.2, 172.16.5.20, and 172.16.5.100, okay? Those all essentially came from the same /24 subnet, but as virtual tunnel endpoints, they are exclusively /32s. So that means there's an IP used for reachability on every one of these switches. It's assigned by the APIC. And then what happens is these guys actually run a routing protocol in here. It's the ISIS routing protocol. And all ISIS is doing is advertising the reachability of those virtual tunnel endpoints. So that each one of these switches is going to build, we call it, it's a routing table, right? But we actually call it an infrastructure ver. And it's going to list the reachability. So for example, spine 1 is going to list spine 2, spine 3, lead 1, lead 2, lead 3, and lead 4. And it's just going to use a standard ISIS topological database, Dijkstra algorithm, and it's going to result in the least cost path to each one of the other infrastructure nodes, each of the other 9 Ks. Now from spine 1, by the way, to get to spine 2, how many different paths are there? In this case, whoops, there's actually 4 different paths from spine 1 to get to spine 2. And just as in any equal cost multipathing environment, we're going to list, to get to spine 2, you can go out interface 1, interface 2, interface 3, or interface 4. And you'll be able to load balance across all those 40 gig links, and in the future they're going to be 100 gig links to get to spine 2. So it's all routing. Okay, there's no layer 2, which is why we don't have to have any loop prevention here, because fundamentally this is all just a layer 3 infrastructure. Now because it's VXLAN, this is basically the VXLAN routing table, right? This is the reachability from each node to every other node. When, let's say that server 1 has the IP of 10.1.1.1/32. It also has a default gateway set of 10.1.1.254. Does that make sense? And let's say server 2 is 192.168.5.1/24, by the way, /24, and it's got a default gateway of .254 on that subnet. Okay? soon as that node appears, because in the APIC, we're going to actually pre-configure the APIC to know those, to expect those subnets to appear. The APIC will actually turn the leaves into default gateways dynamically. And you can have the same default gateway on multiple leaves simultaneously. So if server 3 is also 10.1.1 subnet, and it has the same .254 default gateway, leaf 1 and leaf 2 can both be the .254 gateway at the same time. No problem. And there's no need for HSRP. There's no HSRP running here. This is called an anycast or a pervasive gateway. It's everywhere that it needs to be. All right? And it's only going to be on the leaves that require it to support nodes that are looking for that specific gateway. So in any case, let's go back to server 1 wants to send packets to server 2. Okay? Not server 3. I'm going to erase server 3 from the picture for now. So server 1 wants to talk to server 2. It's going to create an IP packet. Let me erase this. With the destination IP address of 192.168.5.1, source of 10.1.1.1. Server checks its own routing table, realizes it needs to send it to the default gateway. It arcs for its default gateway. It gets a response back from the leaf, which gives it its MAC address of the default gateway. And server 1 puts it into an Ethernet frame with the MAC address of the leaf. It comes in on the leaf. The leaf says, thank you very much. It strips off the Ethernet header. It reads the destination IP address. And then it sends a message to the spine asking, actually, I'm kind of lying when I say that, but there's a mechanism in the fabric whereby leaf 1 is able to resolve that this destination IP over here, right, server 2 is where we're trying to get. Its IP address is known as well, along with its MAC address, as living off of leaf 3. And so then what ends up happening is that leaf 1 will build a tunnel, a VXLAN tunnel. It'll put the original packet into another VXLAN packet with the destination of 172.16.5.20, and it will route that packet to the other leaf. So you see the underlay allows us to create reachability between any leaves that we so choose. And it has nothing to do with any further routing besides the routing that happens between the server and the edge or leaf switch that it connects to. All reachability in this environment, ladies and gentlemen, is defined only by policies that are configured on the APIC. As long as you've got a policy that says that those two servers can talk, a VXLAN tunnel will be built between those leaves and the traffic will be able to flow. Now the reason, again, this is beneficial is because you don't need to go around configuring VLANs, QoS policy, and firewall policy every time you want to stand up a new service. If the server team comes to you and they say, we want to deploy a new XYZ application, you go into your policy database, you create a new EPG for your XYZ app, you create an application networking profile which says who it's allowed to talk to, what other servers or services, endpoint groups it's allowed to talk to. You define the endpoint group by whatever set of characteristics you want, and as soon as that new server appears, no VLAN configuration, no quality of service, no security, it all happens dynamically from there on out. Wherever that server appears on the fabric, the policy will be pushed to the leaf from the APIC to support it. Now where this gets even better, you guys, is that we can integrate with the hypervisor. So let's say that actually servers 1 and 3 maybe are not bare metal standalone servers as I've been sort of depicting them to be thus far, but instead they're VMware servers, and actually I'm probably not going to be able to back up my history all the way here, so I'm just going to erase some stuff down here. What will happen is that, let's say this is an ESXi server, and this is an ENSXi server, okay? And I want these guys to be in what we call the same VMM domain. switch, and you're going to define the port groups that show up in vCenter on the APIC. And your port groups are going to map to EPGs. So when you create an EPG, it'll automatically create a port group. It'll push that port group to the virtual distributed switch in VMware. And then your vCenter administrator just deploys the VM. They say what port group it's in, and it's automatically a part of an EPG. And as long as that EPG has already been defined in terms of reachability as a policy, away you go, right? Again, there's no more configuration of VLANs and edge interfaces and quality of service and security for each and every new app, depending upon where it connects. If that VM vMotions over to the other switch, or if you expanded your VMM domain to include these other servers, and you move your VM over there to server 2, the policy is going to follow it. If it needs a gateway now on leaf 3, it'll instantiate that gateway dynamically. If we disinstantiate or remove that virtual machine from the environment, any and all policy associated for it will disappear as well. So you have highly efficient leaves that are able to instantiate or uninstantiate policy on the fly. So you can define your EPG, call it web, and then anytime your VM administrators deploy web servers, they're automatically your policies are set up. And then the other cool thing about this is that in your application networking profile, you can say that reachability is only based on certain ports. So it's kind of like an access list, right? So you can say, I only want port 80 traffic or port 443 or whatever it is. That's called a filter. You're able to include QoS policies in these contracts between endpoint groups, which can either guarantee, you can mark traffic, you can classify traffic, you can reserve bandwidth, or you can rate limit bandwidth through your QoS policies. And then lastly, what else you can do is you can actually say in the contract, right? So let's say again you've got a contract, you set up an application networking profile. I'm going to call this example again. And in it you say EPG web is allowed to consume services from EPG app. Oh, and by the way, even though I didn't draw it in, one of these leaves has a connection out to your WAN. And we're going to create an EPG for users. Okay? Your users are out here on your WAN. This is called an external connection. It's either going to be layer 2 or layer 3. You're going to create an EPG for users. They're allowed to consume web. But you probably want that traffic to go through a firewall. So I'm going to add a firewall here. And it's a checkpoint firewall. In the contract, within your ANP, okay, we're looking down here again. Here's your ANP. You can actually say that you want the traffic to flow through the checkpoint firewall before it hits the web server. So if I add the firewall, as I did to leaf 4, here's my checkpoint firewall. When my traffic comes in from the WAN, it'll have to go through the firewall before it can hit some VM web in your VMM domain. And this redirection exists inside of my contract. We actually call it a service graph. And you're able to do this in your application networking profile, and you're able to do that not only for firewalls, but also for load balancers. And one of the biggest supported load balancers in the ACI environment is the F5 load balancer. But there are actually dozens, if not hundreds, of third-party appliances that are supported on the ACI fabric. It just so happens Checkpoint, Palo Alto, and F5, and the Citrix NetScaler are the big ones. That we find those services in most enterprise environments. And so you could even say, I want the traffic to flow not only through a firewall, but in that service graph, wanted to hit, then I wanted to hit the load balancer. So the traffic comes in from the WAN, goes through the firewall, then goes to the load balancer, then hits your web server. And then, of course, maybe your web server is consuming services from an app server. All of that is actually defined in your policy. And then here's the coolest thing of all. The APIC is going to be fully integrated with that F5 load balancer or that checkpoint firewall. You don't even need to go into the checkpoint firewall or the F5 load balancer to configure it. When you actually, once you get the APIC and the firewall or the load balancer talking to each other, once you create an application networking profile, it actually goes into the F5 or the checkpoint and it will create the new policy. You don't even need to log into that equipment. And there's a whole ecosystem, again, of vendors whose products work in the ACI fabric. Northbound, just FYI, from the APIC, we support connections to anything that supports what's known as a RESTful API, which also means that you can do all sorts of automation using Python, XML, JSON, Ansible, Puppet, Chef, OpenStack, vCloud Director, UCS Director, anything that can talk, RESTful API can actually program the APIC remotely. So there are a lot of deployments these days that we're seeing with an OpenStack controller, because OpenStack is an even higher level orchestration tool because it's going to organize your VMs, you're going to deploy your VMs, and you're going to be able to allocate storage on demand. And you can use it to create policies in your ACI infrastructure. OpenStack talks to the APIC with a plugin that allows you to actually create the policies in OpenStack. Questions or comments, guys? Actually, there's one from Alan up here. Will the APIC policies take the place of firewall rules? Yes. They will become firewall. They will translate to firewall rules automatically. All right, now, F5 is one of the products that, right out of the gate, had one of these device packages that integrate to the ACI fabric. And if you guys are F5 either big IP or big IQ users, we actually have a partner who's running an F5 webinar. Like, this is an ACI webinar. We have a partner who's running an F5 webinar. And if you're interested in learning more about the F5 big IP, the topics include high availability, command line config, IAPS, how F5 works with AJAX web apps, and defining your local traffic policies. You can actually sign up for a webinar to go over the F5 big IP. Now, this is not going to get into ACI or ACI integration, but if you just happen to have an F5 shop and you want to learn more about F5 and the changes in version 1.1 and 1.2, or 11 and 12, versions 11 and 12, with a focus on local traffic manager, then the link for signing up for that webinar is listed here. It's sunsetlearning.com/technology/F5, and that's on Friday, May 20th. You guys can see the information there. If you need more information on that, just let us know. All right, lastly, I want to say this, which is that despite the complexity that you see here in this environment, right, and there are some paradigm shifts, right, so it is important for you guys to learn a little bit about the XLAN. That's probably the most important thing. And then there are complexities associated with, or not complexities, but new things to do in terms of integrating your APIC with your hypervisors, as well as with your layer 4 through 7 services. And then there are things we can do to set up layer 2 external routing and switching, I should say layer 2 and layer 3 switching and routing connectivity. But for the most part, when we're doing troubleshooting, we can log right in to the switches, and we use things operating system show commands. We actually have a shell for Nexus operating system. You can go in on the switches, and you're going to see the same things. You're going to see VERFs, you're going to see VLANs, you're going to see switch virtual interfaces. What's going to be new is, there are going to be some VXLAN terms, but it's still all the same routing and switching under the covers, right? There's ISIS routing for the infrastructure. There are going to be VTEPs that enable the VXLAN underlay. And then there's going to be higher level routing services if we want to run OSPF or EIGRP or BGP at the edge. But all the stuff that we know as network engineers is still valid, in fact crucial. What's new is just the policy-based approach, and that reachability is based on a slightly different paradigm. All so that everything can be automated ahead of time, and you don't have to go make manual changes every time you stand up a new service on the network. In addition to that, it's fully programmable. It works with things like Python and Puppet and Chef and Ansible.